Every diagram of an atom you were ever shown told you the same story. A nucleus in the middle, electrons going around it, everything built out of small, hard pieces, with the pieces getting smaller until you reach ones that cannot be divided. It is a good picture. It is also, according to the framework physics has used every working day since the 1940s, wrong in a way that is hard to overstate. Here is what the diagram left out. Every electron ever measured is identical to every other electron, with no spread and no variation, matched to 13 decimal places on its magnetic strength and to 21 decimal places on its charge, a sameness no manufacturing process could produce. Particles are created out of nothing and destroyed again by the trillion, on purpose, inside hospital scanners, and it has been proved that no experiment can say where any of them is. There is one idea that accounts for all of that at once, and it says there are no particles. By the end of tonight, you will know exactly what is there instead, and what it makes you. Get cozy. Subscribe if you haven't yet, because by the end of this, the sentence "the atoms in my body" will have nothing left to refer to. Now, let's slowly ease into this. Part 1. The sameness that should not be possible. There is a fact about the world so ordinary that almost nobody stops to look at it, and once you do stop, it becomes very difficult to look away. Every electron in the universe is exactly the same as every other electron in the universe. Not similar, not close, not manufactured to some very fine tolerance by a process we do not yet understand. The same, in a sense that is stronger and stranger than anything the word usually carries. The electron inside the screen you might be falling asleep to, and the electron inside a star 40,000 light-years from here, on the far side of the galactic center, have the same mass to the limits of measurement, the same electric charge to the limits of measurement, and the same magnetic behavior to the limits of measurement. And the limits of measurement here are not vague. The magnetic property of the electron, the quantity physicists call the G factor, has been pinned down to roughly 1 part in 10 to the 13th. That is 13 decimal places. If you were measuring the distance from your front door to the moon with that precision, your uncertainty would be smaller than the width of a human hair. Now, the important part of that is not the precision itself. The important part is what the precision did not find. When you measure something to 13 decimal places across many separate measurements on many separate electrons, you have the opportunity to discover a spread. You have the opportunity to find that this electron is very slightly heavier than that one, that this one carries a whisper more charge, that there is a distribution with a center and edges the way there is for absolutely everything else in the physical world. And there is nothing, no spread, no distribution, no population variance at all. The uncertainty in the number is the uncertainty of the instrument, not the uncertainty of the electrons. The same is true of charge, and there the comparison is even sharper. The magnitude of the electron's negative charge is equal to the magnitude of the proton's positive charge, and experiments have bounded any difference between them to below about 1 part in 10 to the 21st. That is a 21-digit statement about 2 objects that could not be more different from each other in any other respect. A proton is roughly 1,836 times heavier than an electron. A proton is a composite object with internal structure, made of quarks bound by an enormously strong force. An electron, as far as anyone has ever been able to determine, has no internal structure whatsoever, and yet their charges match to 21 decimal places. Sit with how odd that is by comparing it to anything else you have ever handled. Take 2 ball bearings off the same production line, made by the same machine, on the same afternoon, from the same batch of steel. Weigh them precisely enough, and they will differ. They have to differ. They were made, and making things introduces variation. Take 2 grains of sand, and the differences are so large you can see them. Take two snowflakes, and the differences have become a cliché. Every object you have ever encountered carries a history in its differences, a record of how it came to be that particular object, rather than some other one. That is what it means to be a thing. Things have histories, and histories leave traces, and traces are variation. Electrons have no traces, they carry no record. There is no such thing as an old electron, or a new one, an electron from this galaxy, or that one, an electron with a rougher finish, because it was made in a hurry. There is nothing to distinguish them, and I want to be precise about what that means, because the everyday version of the sentence is much weaker than the physics version. The everyday version is that we cannot tell them apart. The physics version is that there is nothing there to tell apart. Electrons have no serial numbers. Not hidden ones, not ones we have failed to read. There is no place in the structure of the world where a serial number could be written. This is the fact I want to build the next 2 hours on, because it is a fact that demands an explanation, and the explanation you were probably given as a child cannot supply one. The picture most of us carry is that matter is made of small things, and the small things are made of smaller things, and eventually you reach the smallest things, which are indivisible, and those are the particles, atoms, made of protons and neutrons and electrons, protons and neutrons made of quarks. Quarks and electrons at the bottom, tiny, hard, final. It is a good picture in the sense that it is easy to hold and it gets a lot of chemistry right. It is a picture of the world as a very large number of very small objects. But now ask that picture the question we just raised. Why are all the electrons the same? And the picture has no answer. If electrons are objects, then something made them, and whatever made them made an enormous number of them, and there is no manufacturing process in physics or anywhere else that produces 10 to the 80th of anything without a single deviation. The object picture can describe the sameness. It cannot explain it. It has to accept it as a brute fact, a coincidence of unimaginable scale, and move on. There is another picture, and under that picture the question dissolves so completely that it stops being a question at all. Under that picture, the sameness is not a coincidence and not an achievement. It is a consequence of what an electron is, and it could not have come out any other way. That picture is the one this whole video is about. It is the framework underneath essentially all of modern physics except gravity. It is the mathematics behind every particle accelerator ever built, behind the design of transistors and lasers, behind the most precisely verified numerical predictions human beings have ever made about anything. Physicists have used it every working day since the late 1940s, and its central claim, stated plainly, is a claim almost nobody outside physics has ever been told. The claim is that there are no particles. I am going to spend the rest of tonight unpacking what that sentence means, what forced physics into it, what evidence there is that it is true, how many of these things there turn out to be when you actually count, and what the framework quietly admits about itself when you push it. And by the end I am going to tell you what it makes you, which is the part I suspect you will still be thinking about tomorrow. But we cannot start there. We have to start somewhere much earlier, with a man who had almost no mathematics, a pile of iron filings, and a suspicion that the space around a magnet was not empty. Part 2. The thing that survived, the death of its own medium. Michael Faraday was a bookbinder's apprentice who never learned much formal mathematics, and in the 1830s he was doing something that most of the natural philosophers of his day found faintly embarrassing. He was scattering iron filings on paper, holding magnets underneath, and staring at the patterns. You have almost certainly done the same thing at some point, and the pattern is familiar. The filings arrange themselves into curved arcs, sweeping from one pole around to the other. What Faraday concluded from those arcs was not what his contemporaries concluded. The prevailing view was that magnets and charges acted on each other at a distance, instantaneously, across empty space, the way Newton's gravity was understood to act. Space itself was a stage. Nothing was happening in it. Faraday thought that was wrong. He thought the arcs were showing him something physically present. He called them lines of force, and he meant it literally. He believed the space around a magnet was in a state, that the state was real, that it extended outward whether or not any iron filings happened to be there to reveal it, and that a second magnet, brought nearby, responded to that local state, rather than reaching across the gap to feel the first magnet directly. Nothing acted at a distance. Everything acted on what was immediately next to it, and the influence propagated through the intervening space. This was, at the time, close to a religious conviction dressed as a scientific one. Faraday could not write it down. He had the idea and no equations, and in 19th century physics, an idea without equations was a very hard thing to defend. James Clerk Maxwell supplied the equations between 1861 and 1865. He took Faraday's picture seriously enough to give it mathematical form, and what he produced was a set of relations describing how electric and magnetic conditions at each point in space change in response to conditions at neighboring points. It is worth pausing on that structure because it is the whole idea in miniature. The equations do not talk about magnets. They talk about what is happening at every point, everywhere, all the time, and how each point pushes on its neighbors. And then Maxwell noticed something he had not gone looking for. His equations permitted a self-sustaining disturbance. A changing electric condition creates a magnetic one, and a changing magnetic condition creates an electric one, and if you set that going, it feeds itself and travels. He calculated the speed at which it would travel, using nothing but two constants measured in laboratory experiments about currents and static charges, quantities that had nothing to do with optics. The number that came out matched the measured speed of light. Light was a disturbance in this thing. That was the moment two entirely separate departments of physics collapsed into one, and it was done not by an experiment, but by noticing what the mathematics was already saying. So by the 1870s, the field had earned its place, but it had also inherited a problem, and the problem was a very reasonable question. A disturbance in what? Every wave anyone had ever studied was a wave in something. Sound is a wave in air. Take the air away, and there is no sound. Ripples are waves in water. A wave is a pattern of movement in a medium, and if you remove the medium, there is nothing left to wave. So if light is a wave, there must be a medium filling all of space for it to be a wave in, including the space between here and the sun, and the space between here and the most distant galaxy. That medium was called the luminiferous ether, and for several decades it was simply assumed. The only remaining task was to detect it. In 1887, Albert Michelson and Edward Morley set out to do exactly that, in a basement in Cleveland, with an apparatus floating on a pool of mercury, so it could be rotated smoothly, without vibration. The logic was simple. The Earth is moving through space at about 30 kilometers per second in its orbit. If space is filled with a medium, the Earth must be moving through that medium, and light traveling with the flow should take a measurably different time to make a round trip than light traveling across it. Split a beam, send the halves along two perpendicular arms, bring them back together, and look at how the interference pattern shifts as you rotate the whole thing. The apparatus was sensitive enough. The result was nothing. No shift. They repeated it at different times of day and different times of year, in case the Earth's motion happened to cancel the ether's motion at one particular moment, and it was nothing every time. It has been repeated with ever-increasing precision ever since, and it has been nothing every time since as well. It remains one of the most consequential negative results in the history of science. Physics did not give the ether up gracefully, and it is worth knowing how hard it fought, because the fight tells you how much was at stake. George Fitzgerald and Hendrik Lorentz independently proposed that the apparatus itself contracted along the direction of motion by exactly the amount needed to hide the effect. This sounds like special pleading, and at the time it partly was. But the contraction factor they wrote down turned out to be correct, and survives in relativity to this day. Others proposed that the Earth dragged a layer of ether along with it, which then had to be reconciled with the observed aberration of starlight, and could not be. Every repair introduced a new requirement, and each new requirement made the medium more elaborate and less detectable, until what remained was a substance whose only property was that it could not be found. Now here is the part I find genuinely strange, and it is the part that sets up everything that follows. Physics did not respond to that result by abandoning the field. It abandoned the medium and kept the field. Think about what that actually amounts to. The field was introduced as a description of the state of a medium. The medium was then shown not to exist. And rather than concluding that the field had been a useful fiction all along, physics concluded the opposite, that the field is the thing that exists, and it never needed a medium in the first place. The electromagnetic field is not a description of what some underlying substance is doing. There is no underlying substance. The field is the substance. It is a physical entity in its own right, present at every point in space, carrying energy and momentum, and capable of vibrating with nothing beneath it doing the vibrating. That should have been a warning, and in a sense it was. It is the first time physics took a thing everyone assumed was an object and replaced it with a pattern that has no object underneath. It would not be the last. There is a way of holding this that I am going to keep returning to tonight, so let me put it down now. Think of a field as a single instrument that exists everywhere at once. Not a lot of small instruments scattered through space, but one continuous instrument occupying all of it, extending through the room you are in and out, past the walls and up through the atmosphere, without a seam. It can be quiet or it can be sounding. When it sounds, we detect something. When it is quiet, we say the region is empty. Hold on to that image, because in the next part something happens to it that Faraday and Maxwell never saw coming. The instrument turns out to have a restriction built into it. It cannot be played at any volume you like. Part 3. Why the ripples come in whole numbers. To see what happened next, I want you to build something in your mind, and then I want you to try to break it. Picture the room you are in, and then take away everything in it, not just the furniture and the air, but the objects entirely, until there is nothing but the space. Now fill that space with a structure. Imagine that at every point there is a small weight, and that every weight is connected by a spring to the weights immediately around it, in every direction, above, below, to each side, and diagonally. The structure has no edges. It carries on past the walls, out through the roof, past the atmosphere, out between the stars, without a join anywhere. It is one object, and it is everywhere. Now reach out and disturb it. Push one of the weights. What you would expect is a ripple. The weight you pushed pulls on its neighbors, they pull on theirs, and a disturbance travels outward through the structure at some speed. And you would expect to be able to push as gently or as hard as you like. A small push, a small ripple. A slightly larger push, a slightly larger ripple. Continuous, like water. That is not what happens. The structure will not accept an arbitrary amount of energy. It will accept 1 unit, or 2 units, or 17 units, and it will not accept anything in between. Push it with less than 1 unit, and nothing happens at all. No small ripple, no faint disturbance, nothing. The energy will not go in. Push it with exactly 1 unit, and something appears in the structure that was not there before. A discrete, self-contained excitation, carrying a definite energy, and a definite momentum. And if you have some instrument capable of noticing it, the instrument registers exactly one arrival, not a partial arrival, not a weak one. One. Try to break it. Try to put in half a unit, and then a third, and then 100th. Nothing takes. The structure sits there, entirely unmoved, absorbing none of it, until you reach the threshold, at which point it accepts the whole unit at once, and not a fraction less. And when you stop pushing, and let the excitation drain away, it does not fade. It does not dim gradually toward nothing, the way a struck bell fades. It goes from 1 to 0, in a single step, with no intermediate state. That excitation, that single indivisible unit of disturbance in the everywhere structure, is what we call a particle. I want to be careful here, because this is the exact point where the picture flips, and if it goes past too quickly, the whole rest of the video will sound like decoration. The word particle has changed jobs. In the picture most of us grew up with, particle names a thing, a small object with a location, moving through space. In this picture, particle names an amount. It is the name for one unit of excitation in something that was already there and always there, filling the room. The electron is not a small object traveling through the room. The electron is what the electron field is doing when it carries exactly one unit. And now go back to the question I left standing at the end of the first part, because it answers itself without any effort at all. Why is every electron identical to every other electron? Because there is one electron field, and the field has one lowest kind of excitation, and every electron anywhere in the universe is that same excitation happening in a different place. Asking why two electrons have the same mass is like asking why two middle Cs played on the same string have the same pitch. There is nothing to explain. It is the same string. There is only one string, and it goes everywhere. Electrons have no serial numbers because there is nothing to write a serial number on. The field is not a factory turning out units. The field is one object, and the units are things it does. This is not an obscure laboratory subtlety either. It is why a photodetector clicks. If light were a continuous wave, a very dim source would deliver its energy smoothly, and a sensitive detector would respond with a smooth, faint, continuous signal. That is not what a photomultiplier does. Turn a source down far enough, and the output does not get quieter. It gets sparser. You get individual, full-sized clicks, separated by longer and longer silences. The size of each click does not depend on how dim the source is, only the rate does. Anyone who has sat in a dark laboratory listening to a single photon counter has heard the whole number rule directly, as a sound. This idea did not arrive fully formed. It arrived in pieces, over about 25 years, and the pieces are worth naming because each one was resisted. The first piece was Max Planck in 1900. Working on a stubborn problem about the light emitted by hot objects. The classical theory predicted, in the shortest wavelengths, an infinite amount of radiated energy, which was so obviously wrong that the failure got its own name. Planck found that he could produce the correct curve if he assumed the energy came in discrete packets proportional to frequency, with a constant of proportionality he introduced for the purpose. He regarded this for years as a mathematical trick, a way to get the arithmetic to come out, not a statement about the world. The second piece was Albert Einstein in 1905, in one of the papers he published that year, arguing that the packets were not a trick. He applied them to the photoelectric effect, where light shining on a metal knocks electrons out of it, and where the behavior is stubbornly wrong if light is a continuous wave. Brighter light should knock electrons out harder. It does not. It knocks out more of them at the same energy, and whether it knocks out any at all depends only on the frequency. That is exactly what you would expect if the light arrives in discrete packets, each carrying an energy set by frequency, each interacting with one electron at a time. It was this paper, not relativity, that earned Einstein the Nobel Prize. The third piece is the one that closes the loop, and it belongs to Paul Dirac in 1927. Planck and Einstein had shown that light comes in units. Dirac showed why. He took Maxwell's electromagnetic field, the continuous everywhere thing that had survived the death of the ether, and applied the rules of quantum mechanics to it directly. The field, treated quantum mechanically, turns out to be exactly the structure I asked you to build a few minutes ago. It can only carry energy in discrete units, and one unit is a photon. That paper is where quantum field theory begins, and it changed what emission and absorption mean. In the old picture, an atom emitting light releases a small object that was somehow stored inside it, and an atom absorbing light captures a small object and puts it away. In the new picture, nothing is stored anywhere, and nothing is transported. The atom de-excites, and the electromagnetic field excites. A photon is created, in the strict sense that there was no photon, and then there was one. When the light is absorbed elsewhere, that photon is not put into storage. It is destroyed. The field returns to quiet, and the energy goes into the absorbing atom. Every source of light you have ever seen has been a field being made to sound. Every shadow has been the field staying quiet. There is one more property of the structure worth flagging now, because it comes back later tonight and it unsettles people. The quiet state is not motionless. A quantum oscillator cannot be perfectly still, because perfect stillness would mean knowing both its position and its motion exactly, and the uncertainty relation forbids that combination. So the lowest state the field can occupy still has energy in it. What we call empty space is the everywhere structure in its quietest possible configuration, and its quietest possible configuration is not nothing. Keep that in your pocket. We will need it. Once you have this picture, several things follow that nobody was aiming at, and the first of them is the strangest, because it arrived as an unwanted piece of algebra that would not go away. A young physicist in Cambridge wrote down an equation for the electron, checked that it worked, and then found it had solutions, describing something that had no business existing. Part 4. The prediction nobody wanted. In 1928, Paul Dirac was trying to solve a specific technical problem, and he had no intention of predicting a new form of matter. Quantum mechanics, as it existed then, did not respect special relativity. The equation everyone was using for the electron treated time and space differently, which is exactly the thing relativity forbids. Dirac wanted an equation for the electron that both theories could live with. He found one. It is 4 lines long. It is engraved on his memorial stone in Westminster Abbey, and it worked immediately, and better than it had any right to. It reproduced the electron's spin, which had been put into the older theory by hand, as an observed fact, with no explanation. Dirac's equation did not have spin inserted into it. Spin fell out of it, as a consequence of demanding that the electron behave correctly under relativity. It also predicted the electron's magnetic strength, the G factor from the first part of this video, and got a value of 2, which was close to the measured value, and had previously been a mystery. So the equation was a triumph, and it had a defect that Dirac could not remove. Along with the solutions describing an electron with positive energy, the equation produced an equal number of solutions describing something with negative energy. Not slightly negative, arbitrarily negative, all the way down without limit. This was not a rounding problem. In quantum mechanics, if a lower energy state exists, a system will find its way there. So every electron in the universe should immediately cascade downward through the negative states, radiating energy as it fell, forever, and all of matter should have disintegrated in a flash of light in a fraction of a second. Since matter had visibly not done that, something was wrong. Dirac's first attempt to fix it was one of the strangest ideas anyone has proposed in physics, and I have some affection for it. He suggested that all the negative energy states are already full, every one of them, everywhere, occupied. Since electrons obey a rule forbidding two of them from sharing a state, we will come back to that rule properly later, because it is doing more work in your life than you realize. A positive energy electron cannot fall into a negative state, because there is nowhere to fall to. Every seat is taken. The universe is filled, invisibly and uniformly, with an infinite ocean of occupied states, and we do not notice it for the same reason a fish does not notice water. The picture had a consequence Dirac could not avoid. If you gave one of the electrons in that ocean enough energy, you could lift it out into a positive energy state, and it would appear as an ordinary electron. But you would also leave behind a gap in the ocean where it had been, and a gap in a uniform sea of negative charge behaves, to any instrument, exactly like a positive charge moving around. Dirac initially hoped the gap was the proton. It was the only positive particle anyone knew about, and it would have been very tidy. It was also badly wrong, and Hermann Weyl pointed out the reason. Symmetry demands that the whole have the same mass as the electron, and the proton is about 1836 times heavier. There was no way around it. So in 1931, Dirac took the step that mattered, and wrote that the whole must be a new kind of particle, unknown to experiment, with the mass of an electron and the opposite charge. He called it an anti-electron. This was, at the time, an outrageous thing to publish. Nobody had seen such a thing. There was no experimental hint of it, no anomaly it explained, no gap in the data it filled. It was demanded by an equation, and by nothing else. It is worth registering how uncomfortable this made everyone, including Dirac. Werner Heisenberg wrote to Wolfgang Pauli that the saddest chapter of modern physics was the Dirac theory, and Pauli formulated a joke rule of his own about theorists' equipment breaking whenever they entered a laboratory. Dirac himself hedged in print for 3 years. The equation had done something no equation was supposed to do. It had made a claim about what exists rather than describing what had already been found, and the profession did not have a comfortable way to respond to that. 18 months later, at Caltech, a 27-year-old experimentalist named Carl Anderson was photographing cosmic rays. His apparatus was a cloud chamber inside a strong magnetic field. Charged particles passing through the chamber leave a trail of condensation, and the magnetic field bends the trail, one way for positive charges, the other way for negative. Anderson was not looking for anti-electrons. He was surveying what came down out of the sky. On the 2nd of August 1932, he took a photograph of a track curving the wrong way. The curvature was too gentle for a proton, and the track was too long and too light. It looked, in every measurable respect, like an electron going backwards. There was an obvious objection, and Anderson had already anticipated it. A negative electron traveling downward and a positive particle traveling upward produce identical curvature. You cannot tell them apart from the track alone. So Anderson had placed a lid plate 6 millimeters thick across the middle of the chamber. Any particle crossing it would lose energy, and a particle with less energy curves more tightly. By comparing the curvature above and below the plate, he could establish which way the thing had been going. The photograph settled it. The track was tighter after the plate than before it, on the side that meant the particle was moving upward, and it carried a positive charge with the mass of an electron. Anderson published in 1933. The positron, as it came to be called, was the first antiparticle anyone had ever seen, and Anderson received the Nobel Prize for it in 1936, 4 years after the photograph, and 5 years after Dirac had written the thing down without evidence. Anderson's photograph was not the only relevant evidence, and the story has a footnote that is usually left out. In Cambridge, Patrick Blackett and Giuseppe Occhialini were running a cloud chamber triggered by coincidence counters, so that it photographed only when a cosmic ray had actually passed through, rather than photographing constantly and hoping. Their method produced far more usable images than Anderson's, and they had positron tracks in hand at around the same time. They held back from publishing until they were certain, and Anderson, working faster and with less caution, got there first. Blackett and Occhialini's paper the following year did something Anderson's did not. It explicitly connected the observation to Dirac's prediction, and it showed positrons being produced in pairs alongside electrons, which turned out to be the more important observation of the two, for reasons the next part of tonight will make clear. I want to make sure the shape of this lands, because it is the first hard evidence that the framework we are building is not just a way of talking. The order of events was not, we found a strange particle, and then we worked out a theory that could accommodate it. The order was the reverse. The mathematics required a thing that nobody wanted, that had no observational support, and that its own author initially tried to explain away as a proton, and the thing was there. The negative energy ocean, incidentally, did not survive. It was a scaffold, and once quantum field theory was properly formulated in the following decades, the scaffold came down. In the field picture, you do not need an infinite sea of occupied states, because you are not tracking individual electrons in the first place. The electron field simply supports two kinds of excitation, one carrying negative charge and one carrying positive charge, and every field with matter-like behavior does the same. Antimatter is not a hole in anything. It is the other thing the field can do. That reformulation cleaned up the mathematics. It also removed the last defense of an idea that most people still hold without examining it. The idea that the number of particles in the world is a fixed quantity. Part 5. Nothing stays. Almost every intuition you have about matter contains a hidden assumption, and the assumption is so basic that it is difficult to notice you are making it. The assumption is that stuff is conserved. Things can move, combine, break apart, change form. But the count is stable. You do not get more of them out of nowhere, and they do not vanish. In ordinary quantum mechanics, the version taught first, the one with the wave function and the hydrogen atom, that assumption is built into the mathematics. You specify a system with a certain number of particles, and you solve for how that system evolves. The number never changes, because there is no place in the equation where it could. Quantum field theory abandons it in the first chapter, and it has no choice, because the moment you require both relativity and quantum mechanics, particle number stops being a well-defined constant. Relativity says mass and energy are the same currency. Quantum mechanics says energy in a small region for a short time is not sharply defined. Put those together and you get the following. If enough energy is concentrated in a small enough region, fields that were quiet can become loud, and quanta that did not exist a moment ago can exist now. The cleanest example is pair production. A photon of sufficient energy passing close to an atomic nucleus can vanish, and in its place, an electron and a positron appear. The threshold is precise because it is set by the rest masses that have to be paid for, about 1.022 million electron volts, which is exactly twice the rest energy of an electron. Below that threshold, nothing happens, no matter how many photons you send. The transaction is not affordable. Above it, the transaction goes through, and where there was one massless quantum of the electromagnetic field, there are now two massive quanta of the electron field. The nucleus has to be there, incidentally, and the reason is worth a moment. A photon in genuinely empty space cannot become a pair no matter how energetic it is, because there is no way to satisfy conservation of energy and momentum simultaneously. The nucleus absorbs a small amount of recoil and makes the books balance. The vacuum will not do this on its own. It needs a witness. There is a more extreme version of this that has never been achieved but has been calculated, and it tells you where the boundary sits. Julian Schwinger worked out in 1951 the electric field strength at which empty space would simply break down and start producing electron-positron pairs on its own, with no photon and no nucleus involved, the field pulling the pairs directly out of the vacuum. The number is about 1.3 times 10 to the 18 volts per meter. For comparison, the strongest static electric fields ever sustained in a laboratory are around 10 to the 10th or so volts per meter, which leaves us short by a factor of roughly 100 million. Nobody has broken the vacuum, but the theory is quite clear that it can be broken, and that it would break by producing matter. Run the process backwards and you get annihilation. An electron meeting a positron does not collide in any mechanical sense. Both excitations are simply removed from the electron field, and the electromagnetic field is excited in their place, typically producing two photons of 511,000 electron volts each, flying apart in almost exactly opposite directions. That last sentence describes a piece of hospital equipment. Positron emission tomography works by injecting a patient with a compound tagged with a positron-emitting isotope. The positrons travel a millimeter or two, meet electrons in the surrounding tissue, and annihilate. The two photons head off back to back. A ring of detectors around the patient catches them, and because the pair travels along a straight line through the annihilation point, the machine can reconstruct where the annihilation occurred. Build up enough of them, and you have a three-dimensional image of where the tagged compound accumulated. The near-perfect back-to-back geometry is what makes the reconstruction possible, and the small deviations from a straight 180 degrees caused by the residual motion of the pair are one of the fundamental limits on how sharp such a scan can ever be. So somewhere tonight, in a hospital, matter and antimatter are destroying each other inside a living person, on purpose, as a diagnostic procedure. That is how routine the non-conservation of particle number is. This also quietly resolves something about antimatter that people find eerie. Antiparticles can be described, in the mathematics, as particles moving backwards in time, and this is not a piece of showmanship. It is a statement about how the same field operator appears in the equations depending on which direction the momentum is pointing. A positron traveling forward and an electron traveling backward are, in the formalism, the same object read in two directions. That sounds like a violation of causality, and it is not one, because nothing about it lets any signal reach the past. It is a symmetry of the description, not a loophole in the world. In the mathematics, all of this is handled by two operations. One of them adds a quantum of excitation to a field. The other removes one. Interactions between fields are terms that couple them together, so that removing an excitation from one field can add an excitation to another. That is the entire machinery. Everything that has ever happened in the universe, on this picture, is fields being excited and de-excited by their couplings to other fields. Which means a particle accelerator is not what most people picture. The image people carry is of smashing things to see what smaller things fall out, like breaking open a walnut. That is not what happens. When two protons meet at very high energy at a collider, the outgoing particles are not pieces of the incoming ones. Most of them were not present in any form before the collision. The collision dumped an enormous amount of energy into a very small region, and every field with a coupling to that region and enough energy available got excited. A single proton-proton collision at the Large Hadron Collider routinely produces hundreds of outgoing particles from two incoming ones. Nothing was broken open. Something was made loud. And now I want to draw out the consequence that I think matters most, because it is the one that comes back at the end of tonight. Everyone says my atoms, the atoms in my body, the matter I am made of. It is a possessive, and we use it without thinking, and it has always felt harmless. Quantum field theory removes the possessive completely, and not for the reason you might expect. The familiar version of this point is that your atoms get exchanged with the environment over time, that the material in your body is not the material that was there years ago. That is true, and it is a nice fact, but it is much weaker than what the physics is actually saying. The physics is saying that there is nothing there to own in the first place. There is no individual electron, there is an electron field, and there is a number of excitations in it, and that number changes. Nothing in the theory tracks which excitation is which, because there is no place in the theory where such a record could be kept. If you take an electron out of your hand and put a different one back, the theory does not merely fail to notice. It has no way to state that anything happened, because the sentence I just wrote does not correspond to any physical difference at all. The two situations are not similar. They are the same situation, described twice. So the word my, applied to the smallest constituents of a person, has nothing to attach to. It is a word we have all used our whole lives, about something that turns out not to have owners, because it does not have individuals. That is a strange thing to accept on somebody's say-so. It sounds like the kind of claim that could be philosophy dressed as physics, which raises a fair question, and it is the question the next part is about. Can you actually check it? Can you put the identity of two particles on a laboratory bench and measure whether nature can tell them apart? You can. Somebody did, in 1987, with a half-silvered mirror and two detectors. Part 6. The experiment that measures sameness. The setup is almost insultingly simple, which is part of why it is so convincing. In 1987, at the University of Rochester, Chung Ki-hong, Zhe Yu-o, and Leonard Mandel built the first experiment ever to observe two photons interfering with each other, and the whole thing fits on a table. Picture the bench. The room is dark, because the detectors are sensitive enough that ordinary light would swamp them. In the middle sits a beam splitter, a half-silvered mirror, the same object in principle as the coated glass in a pair of sunglasses, angled at 45 degrees. A photon arriving at it has a 50-50 chance of passing through and a 50-50 chance of reflecting. There are two ways in, one from each side, and two ways out. A single photon comes in from the left, another comes in from the right, arriving at the mirror at as close to the same instant as the apparatus can manage. Two detectors wait at the two exits, and they are wired together into a circuit that does one job. It registers a coincidence, a moment when both detectors fire at the same time. Now think about what should happen, using nothing but ordinary reasoning about small objects. The photon from the left either goes through or bounces. The photon from the right either goes through or bounces. Those are independent choices, so there are four equally likely outcomes. In one, both end up at the left detector. In one, both end up at the right. In the other two, they separate, and both detectors fire. So half the time you should get a coincidence. That is not a subtle prediction. It is just counting. Watch the counter as the experimenters slowly walk the two arrival times into alignment. When the photons arrive at clearly different moments, the coincidence rate sits at about half, exactly as the counting says it should. Then, as the arrival times close in on each other, the rate begins to fall. Not by a little. It falls, and keeps falling, and as the overlap becomes complete, it drops to essentially nothing. The two detectors stop firing together entirely. Both photons are leaving through the same exit every single time, and which exit they choose varies randomly, but they always choose it together. That collapse in the coincidence rate is called the Hong-ou-Mandel dip, and I want to be precise about what causes it, because the obvious explanations are all wrong. Nothing pushed them together. Photons at these energies do not appreciably interact with one another at all. Two beams of light cross without disturbing each other, which is why you can see across a lit room. There is no force here. There is no attraction. Nothing about the mirror changed. What happened is this. There are two ways the apparatus could produce a coincidence. Both photons transmitted, or both photons reflected. In quantum mechanics, you do not add up the probabilities of indistinguishable roots to the same outcome. You add the amplitudes, and then square the total. And when the two photons cannot be told apart in any way, same frequency, same polarization, same arrival time, those two amplitudes are equal in size and opposite in sign, and they cancel, exactly. The outcome is not unlikely. It is removed. There is no root to it left. The cancellation depends entirely on the photons being indistinguishable, and that is what makes this experiment so much more than a curiosity. It is a measurement of sameness, with a dial on it. Make the photons slightly different, offset their arrival times, rotate one polarization relative to the other, shift one frequency, and the two roots stop being identical, the cancellation stops being exact, and coincidences come back in proportion to how distinguishable you made them. The depth of the dip is a direct, continuously variable readout of how identical two photons are. And the depth goes to the bottom, not partway. Under good conditions, the coincidences go away. The dip is narrow, and how narrow tells you something about what is being compared. Its width is set by the coherence time of the photons, the length of the wave packet in time, and in the original experiment, that was a few hundred femtoseconds. A femtosecond is a millionth of a billionth of a second. In a few hundred of them, light travels about a tenth of a millimeter, so the two photons had to arrive within a window corresponding to a distance smaller than the thickness of a fingernail for the effect to appear at all, and outside that window the coincidences came straight back. Later refinements showed that the exact shape of the dip is a mathematical transform of the joint spectral properties of the photon pair, which means the profile of the collapse is itself a readout of the quantum state of the two photons together. I said in the first part of tonight that electrons have no serial numbers, and I said the physics version of that sentence is stronger than the everyday version. This experiment is where the difference becomes something you can measure. The everyday version is that we cannot tell the two photons apart. If that were all that was going on, if each photon secretly were a distinct object, and we simply lacked the equipment to label them, the coincidences would still be there. Our ignorance does not remove roots from the world. The roots are removed because there genuinely are not two distinguishable histories to add up. Nature has no label either. The apparatus is not failing to read the serial number. There is no serial number. The result has held up for nearly 4 decades under increasingly hostile testing. The most important variant removes the last easy objection. The original experiment made both photons in the same crystal at the same moment, so a skeptic could argue that their shared origin was doing the work. So the experiment was repeated with 2 photons from entirely independent sources, produced separately, with no common history, brought together for the first time at the mirror. The dip is still there. 2 photons that have never had anything to do with each other, arriving from different lasers, are as indistinguishable as 2 photons born together. Because sameness is not a fact about their history, it is a fact about what they are. It is worth stepping back to the central claim for a moment, because this is a lot of optics for a video about what reality is made of. The claim was that particles are excitations of fields rather than small objects. The identicalness of particles was the first argument for it, and the objection to that argument has always been that identicalness might be a fact about our instruments rather than a fact about the world. This experiment is the reply. The instruments are not the limitation. The indistinguishability is physical. It has consequences that show up in a counter, and those consequences would not exist if each photon were quietly its own object underneath. The effect has since been scaled up in ways the original authors could not have anticipated. It has been demonstrated in massively parallel form using independent soliton microcombs, generating large numbers of simultaneous two-photon interference events on chip-scale hardware. It has been used backwards, as a timing instrument, resolving arrival time differences far finer than the detector's own timing resolution. It is the standard benchmark by which any single photon source is judged, because indistinguishability is the resource that makes photonic quantum computing possible at all, and the dip is how you measure whether you have it. And there is a mirror image of the result that closes the argument. Photons are bosons, and bosons bunch. Given the option, indistinguishable bosons prefer to end up in the same state, which is why they leave together. Electrons are fermions, and if you run the equivalent experiment with two indistinguishable electrons entering a beam splitter, you get precisely the opposite outcome. They always leave through different exits, every time. The amplitudes cancel for the together outcome instead of the apart outcome, because fermion amplitudes pick up a minus sign under exchange where boson amplitudes do not. That anti-bunching sounds like a technical footnote about a laboratory experiment. It is not a footnote. It is the reason you are not currently falling through the floor. Part 7. Why you do not fall through the floor. Put a hand flat on whatever surface is nearest to you. A mattress, a wall, the arm of a chair. Press down until you feel resistance. Now go inward, past the texture, past the fibers, or the grain, down to the atoms. And when you arrive at the atoms, the first thing to notice is that there is almost nothing there. An atomic nucleus occupies something like 1 part in 10 to the 15th of the volume of its atom. If you scaled a nucleus up to the size of a marble and set it on the ground, the outer edge of the atom would be several hundred meters away in every direction. Everything in between is not thin material. It is not anything. So a solid object, examined closely, is overwhelmingly empty. Your hand is overwhelmingly empty. The surface you are pressing on is overwhelmingly empty. Two clouds of almost nothing are meeting, and something is stopping them. The usual answer is electrical repulsion. Negative electrons in your hand pushing against negative electrons in the surface. That is real, and it contributes, but it is not the dominant effect at contact, and you can see that it cannot be, because atoms are neutral overall. Their positive charges attract, just as their negative charges repel. If electrostatics were the whole story, matter would be far more compressible than it is. The real answer is a rule about sameness, and it is the same rule that produced the anti-bunching at the end of the last part. Wolfgang Pauli proposed it in 1925 as an empirical patch. Atomic spectra made no sense otherwise. If electrons in an atom simply sought the lowest available energy, they would all pile into the innermost orbital and stay there, and every element would behave more or less identically, and there would be no chemistry. Since there very obviously is chemistry, Pauli proposed a prohibition. No two electrons in an atom may occupy the same quantum state. He had no derivation. He had the fact that it worked. 15 years later, he derived it. In 1940, Pauli proved what is now called the spin statistics theorem, and it is one of the most consequential results in the whole framework we have been building tonight. It says that in any relativistic quantum field theory that satisfies a short list of extremely reasonable requirements, that interactions are local, that energies have a floor rather than running down forever, that causes precede effects, the outcome is forced. Fields whose excitations carry half-integer spin must obey antisymmetric statistics, which means exclusion. Fields whose excitations carry whole number spin must obey symmetric statistics, which means bunching. There is no third option and no way to choose. So exclusion is not an extra law bolted onto physics to make the periodic table come out. It is a theorem about what a field with spin 1/2 is permitted to do, given that the universe is relativistic and causal. Electrons exclude each other for the same reason photons bunch, because of what kind of excitation they are. There is a way of stating exclusion that makes its connection to the last part unmistakable. Exchanging two identical fermions multiplies the description of the whole system by -1. That is the formal content of antisymmetry. But notice what kind of statement that is. It is not a claim about an operation you could perform on the world. You cannot swap two electrons, because there is no such thing as this electron and that one to swap. It is a claim about which mathematical descriptions correspond to the same physical situation. The minus sign is a consequence of indistinguishability, and exclusion is a consequence of the minus sign, because if two excitations were in the same state, swapping them would leave the description unchanged and multiply it by -1 at the same time, and the only quantity equal to its own negative is 0. The probability of the configuration is not small. It is exactly 0, for arithmetic reasons. The immediate consequence is the structure of matter. Electrons cannot collapse into the lowest orbital, so they stack. The stacking produces shells, the shells produce valence, valence produces the periodic table, and the periodic table produces chemistry, biology, and you. Every property of every material you have ever handled traces back to the fact that two identical excitations of the electron field are forbidden from sharing a state. And the larger consequence is what is happening under your hand right now. When you press two objects together, you are trying to push two populations of electrons into the same region. Doing that requires putting electrons into states that are already occupied, and that is forbidden. So the only way to proceed is to promote them to higher, unoccupied states. Higher states cost energy. The more you compress, the higher you have to go, and the energy cost climbs steeply. That steeply climbing cost, expressed as a force, is what your hand feels. It is called degeneracy pressure, and it is not a force in the ordinary sense at all. Nothing is pushing. There is no field of repulsion between the surfaces doing the work. There is a prohibition, and the prohibition has an energy price, and the price is what you experience as solidity. Sit with that for a second, because it is one of the strangest true things about ordinary life. You have spent every day of your life supported by floors, and you have never once been held up by anything hard. You have been held up by a rule about sameness, and the rule can lose. This is not a metaphor. Take the same physics and scale it up to a star that has exhausted its fuel and is collapsing under its own gravity, and degeneracy pressure is what stops the collapse. A white dwarf is an object roughly the mass of the sun, compressed to roughly the size of the Earth, and nothing holds it up except electrons refusing to share states. It works, up to a point. Subramanian Chandrasekhar calculated where the point is while he was still a teenager, on a boat from India to England in 1930. Above about 1.4 times the mass of the sun, gravity wins. The electrons cannot be pushed higher fast enough, the resistance fails, and the star collapses further, into a neutron star, where the same rule takes over again, with neutrons doing the excluding, packing a solar mass into a sphere about 20 kilometers across, at roughly the density of an atomic nucleus. Or, if there is too much mass, even for that, into a black hole, where as far as anyone knows, nothing stops it at all. The floor under your bed and the collapse of a dying star are the same physics with different odds. And there is a formal version of this, because for a long time nobody had actually proved that ordinary matter is stable, that a large lump of atoms will not simply collapse in on itself. Freeman Dyson and Andrew Leonard proved it in 1967, and the proof requires exclusion. Without it, the energy of a collection of electrons and nuclei does not scale in proportion to how many you have. It runs away faster. And matter, as we know it, does not hold together. The stability of everything solid is a theorem, and the theorem's key ingredient is that the constituents are indistinguishable. Bosons, meanwhile, do the opposite with the same enthusiasm, and it is worth naming because it shows the rule cuts both ways. Identical bosons prefer to occupy the same state, and given the chance, they will all crowd into the lowest one. That is what a Bose-Einstein condensate is. It is why liquid helium becomes a superfluid and climbs the walls of its container. It is why a laser produces a beam of light, all in one state, rather than a spray of independent photons. Bunching and exclusion are two faces of one theorem, and between them, they account for most of the behavior of matter and light. So, the sameness is real, it is measurable, and it builds the world, which raises a question so obvious it is slightly embarrassing that we have not asked it yet. If everything is made of fields, how many fields are there? Part 8, 17. We are about halfway through, so let me stop and stack up what we have, slowly, because the second half is going to build on all of it. We started with a fact that should not be possible. Every electron is identical to every other, with no spread, no variation, no history. We found that the object picture cannot explain that, and that a different picture explains it without effort, because there is one electron field, and every electron is the same excitation of it. We watched the field concept arrive with Faraday, get its mathematics from Maxwell, and then survive the loss of the medium it was supposed to be a disturbance in, so that the wave outlived the water. We saw what happens when you apply quantum rules to such a thing. It stops accepting energy continuously and starts accepting it in whole units, and one unit is what we have been calling a particle. We watched that framework predict antimatter before anyone had seen it, and watched Anderson photograph it 4 years later. We saw that the number of these excitations is not conserved, that they are created and destroyed routinely, and that hospitals rely on it. We watched 2 photons at a beam splitter demonstrate that the indistinguishability is not a limit of our instruments, but a feature of the world. And we found that the same indistinguishability applied to electrons is the reason the floor holds. That is the case. Reality, at the level physics currently works at, is not a collection of small persistent objects. It is a set of fields, filling everything, and their excitations. Now, how many? That question sounds like it should have a boring answer. It should be a matter of looking it up. And what happens when you actually ask it is the part of tonight I have been looking forward to, because the answer will not sit still, and the way it refuses to sit still tells you more about the state of physics than any single number could. I am going to follow a piece of reporting from June of 2026, in which the science writer Natalie Wolchover emailed several working particle physicists and asked each of them personally how they count. The replies did not agree. They did not agree in interesting ways. Start with the answer on the wall. If you have ever been in a physics classroom, you have seen the chart, the periodic table-shaped poster of the standard model, with the particles in tidy colored squares. There are 17 squares. 12 of them are matter, 3 charged particles that behave like heavier and heavier versions of each other, the electron, the muon, and the tau. 3 neutrinos, 1 paired with each of those, almost massless, barely interacting, passing through the Earth by the trillion every second. And 6 quarks, with the names somebody chose in a good mood: up, down, charm, strange, top, and bottom. 4 of them are forces, or rather, force carriers. The photon, which carries electromagnetism, and which we have been discussing all night. The W and the Z, which carry the weak force, the one responsible for certain kinds of radioactive decay and for the reactions that let the sun burn at all. And the gluon, which carries the strong force and binds quarks into protons and neutrons. It is also worth being precise about what a force carrier is in this framework, because the phrase invites a misleading image. The usual picture is of two particles throwing something back and forth, like skaters passing a ball, and it is not a bad first approximation, but it hides the actual structure. What is really going on is that two fields are coupled in the underlying equations, so that an excitation in one cannot change without disturbing the other. The photon field and the electron field are wired together. Move an electron, and the electromagnetic field must respond, and that response, quantized, is a photon. The force is not a thing being exchanged, the force is the coupling, and the exchanged quantum is what the coupling looks like when you count it. And one of them is neither. The Higgs boson sits by itself, a scalar particle, neither matter nor a force carrier, whose field gives mass to the others through its interactions with them. That is the poster. 17. And it is a real answer, held by real physicists. Melissa Franklin, a particle physicist at Harvard, told Wolchover plainly, "I think 17 is the right answer." The 3x3 arrangement of the matter particles is itself an unsolved problem, worth naming in passing. The muon is a heavier copy of the electron, about 207 times heavier, identical in every other respect, and it decays in about 2 microseconds. The tau is heavier still, roughly 3,500 times the electron's mass, and lives less than a trillionth of a second. The quarks come in the same 3-tier arrangement. Nobody knows why there are 3 tiers. There is no principle in the standard model requiring 3. 2 would work, and so would 7. Isidore Rabi's response when the muon was discovered has never been improved on. Who ordered that? There is also something missing from the poster that is easy not to notice. Gravity is not on it. The standard model describes electromagnetism, the strong force and the weak force, and says nothing whatsoever about gravity, which is not one of the 17 and has no agreed field-theoretic description at all. This is the single largest hole in the claim that everything is a quantum field, and I am going to come back to it before we finish, because honesty requires it. But for the moment, note that the poster is not a picture of everything. It is a picture of everything except the force you are most familiar with. Before the number starts moving, I want to point at 2 things on that poster. The first is you. Of the 17, you are made of 3, up quarks and down quarks, which combine in 3s to make the protons and neutrons in your nuclei, and electrons, which make everything about chemistry work. That is the entire inventory of a human being. 3 fields, doing something complicated. The photon and the gluon are involved constantly, holding it all together, but as excitations, they are not what you are made of. They are what the assembly is mediated by. The other 12 you can live your whole life without ever containing. The second is the Higgs, because it is the cleanest demonstration that these fields are physical entities rather than bookkeeping. The other 16 fields sit at 0 in empty space unless something excites them. The Higgs field does not. It has a non-zero value everywhere, all the time, including in the emptiest volume you can construct, and it is that permanent background value that other particles interact with to acquire mass. It was proposed in 1964. Its ripple, the Higgs boson, the excitation you get when you disturb a field that is already switched on, was announced at CERN on the 4th of July 2012 at a mass of around 125 giga-electron volts. 48 years passed between someone writing that field down on paper and someone photographing the splash when you hit it. Think about the instrument image from earlier. One continuous instrument, everywhere at once. What the poster is telling you is that there are 17 of them, laid over each other in the same space, and that everything that has ever happened is those 17 being played against one another. Every star, every thought, every collision, every chemical reaction in every organism that has ever lived. 17 instruments and their interference. It is a satisfying number. It is finite, it is countable, it fits on a wall. And it is the smallest defensible answer anyone gives. From here the number only goes up, and the first increase happens for a reason we have already met tonight. Part 9. The number will not stay still. The first increase comes from Dirac, and we have already met it. Every matter field supports two kinds of excitation, one with each sign of charge. Relativity requires it. The electron field comes with the positron built in, and there is no way to have one without the other. So the 12 matter particles are not 12, they are 24. The force carriers add to that as well, though less dramatically. The W boson comes in two versions, one positively charged and one negatively charged, and each is the other's antiparticle. The Z, the photon, and the gluon are electrically neutral and do not double. So the 4 becomes 5, and the running total is 24 plus 5 plus 1, which is 30. Franklin does not count it that way. She leaves antiparticles off her list on the grounds that they mathematically mirror the particles and neither can exist without the other, so counting both is double counting. Wolchover's objection is that this rationale does not survive contact with the actual universe. Particles and antiparticles are undeniably distinct. They cannot turn into one another, and far from playing equivalent roles, they play opposite ones. Matter is so overwhelmingly dominant that any antimatter produced anywhere near us finds matter and annihilates almost immediately. Why the universe came out that way, rather than with equal amounts of both cancelling out to leave nothing, is one of the major unsolved problems in physics. Two things that different are not the same thing counted twice. There is a wrinkle here that shows how unfinished this corner of the accounting is. It is not actually settled whether neutrinos have distinct antiparticles at all. If they are what are called Dirac particles, they do, like every other matter field. If they are Majorana particles, each neutrino is its own antiparticle, and the doubling does not apply to them. Experiments hunting for a very rare process called neutrinoless double beta decay are built specifically to answer this, and after decades of searching, nobody has seen it. So a component of the census, 3 fields out of the 12, is currently unknown, not because the counting is hard, but because nature has not yet told us. So, 30, if you are being careful. Then the gluon comes apart in your hands. The poster shows 1 square for the gluon, and that is a simplification serious enough to be called an error. The strong force is not carried by 1 gluon. It is carried by 8, each with a distinct combination of the charges that the strong force responds to, charges that were given color names, red and green and blue, purely because 3 of them combine to a neutral state, the way 3 primary lights combine to white. There is nothing optical about them. Each gluon carries 1 color and 1 anticolor, and there are 8 independent combinations. Whether to count them separately is where the experimentalists and the theorists part company. Experimentally, the 8 gluons are indistinguishable. No measurement can tell you which one you are looking at. And Franklin, an experimentalist, shook her head at the suggestion. But in the equations that define the theory, the 8 are as distinct from one another as the W is from the Z. If you are counting what is in the mathematics, and we have spent all night arguing that the mathematics is where the reality is, consistency says count them. 37. And quarks carry color too. Each quark comes in 3 colors, and each antiquark in 3 anticolors, which means there are not 6 quarks and 6 antiquarks, but 36. Color is not decorative. It is why the strong force works at all, and why isolated quarks are never observed. Stable matter has to be color neutral, which is why a proton contains 1 quark of each color, the way 3 primaries make white. 61. It is worth holding the central point in view while the arithmetic runs, because the arithmetic is not the point. We are not doing bookkeeping for its own sake. The reason the count matters is that we spent the first half of tonight establishing that reality is made of fields rather than objects, and the natural next question, how many kinds are there, is turning out not to have a stable answer. That is not a scandal. It is what happens when the thing you are counting is not a collection of items, but a mathematical structure that can be decomposed in more than one legitimate way. The count depends on how closely you look, and the fact that it does is itself a fact about fields. And then it gets less comfortable, because the next split is one that most popular accounts leave out entirely. Matter particles come in left-handed and right-handed varieties. This is called chirality, and it is not a geometric arrangement like the handedness of a glove. It is a mathematical mirror-image relation between two states that cannot be rotated into each other, any more than your left hand can be rotated into your right. The reason it cannot be dismissed as a technicality is that the weak force does not treat the two the same. The weak force acts only on left-handed matter particles. It ignores the right-handed ones entirely. That is not a small preference. It is one of the most fundamental asymmetries in nature, and it is why neutrinos appear in the Standard Model only in a left-handed form, with no right-handed partner at all. Chris Quigg, a senior theorist at Fermilab, told Wolchover, "I insist on left and right-handed particles. I can't account for this. Blame my parents." There is one more reason the chirality split has to be taken seriously rather than waved through. For a massless particle, chirality and the more intuitive property of helicity, whether the spin points along the direction of motion or against it, are the same thing. For a massive particle they come apart, because you can always overtake a massive particle and see its direction of motion reverse, while its spin does not. That means chirality is not something you can define by watching a particle move. It is a property of how the field enters the equations. And since it is the property the weak force actually responds to, it is not optional. Force carriers have their own version of the same split, called polarization. Photons and gluons come in two polarization states. The W+, the W-, and the Z have three, because they have mass. And the extra longitudinal state has an origin worth noting. Before the Higgs field switched on in the early universe, those extra states belonged to the Higgs field itself, and were absorbed by the weak bosons when the symmetry broke. The standard phrase for this is that the gauge bosons ate them. 3 of the 4 original Higgs components are now the longitudinal modes of the weak force carriers, and only the 4th remains as the Higgs boson we detect. Count every chirality and every polarization state separately, and the total comes to 118. A right-handed, anti-red, anti-charm quark, a green anti-blue, left-polarized gluon, a longitudinally polarized W-. Each of these is a genuinely different thing that behaves differently in the world, and if what you want to count is distinguishable states, 118 is the honest number. So the census stands at 17, or 30, or 37, or 61, or 118, depending on what you think counting means. And this is where David Tong of Cambridge, who had been corresponding with Wolchover throughout, wrote the sentence that gives the rest of this away. Now, he said, comes the weird stuff. Part 10, 995 and a half. The weird stuff arrives by way of a theorem, and the theorem starts with an observation about zooming out. Physicists have a general term for all the ways a system can vary: degrees of freedom. A single weight on a spring, free to move in one direction, has 1. A weight free to move in 3 dimensions has 3. The more independent ways something can change, the more degrees of freedom it has. And there is a pattern in how that number behaves as you change scale. Describe a glass of water at everyday resolution, and you need a handful of variables: temperature, pressure, volume. Zoom in to the molecules and the number of variables explodes. Zoom in further, into the protons and their constituent quarks and their colors, and it explodes again. The closer you get, the more ways there are for things to differ. Pull back, and those distinctions blur together and stop mattering, and the count falls. In 1988, the physicist John Cardy conjectured that this is not just a tendency, but a law. That in any quantum field theory, the number of effective degrees of freedom must decrease as you zoom out, and can never increase. It had already been proved for theories with one dimension of space and one of time, which describe particles moving along a line, whether it held in 3 dimensions of space plus time, which is to say, in the world we live in, and in the Standard Model, was open for over 20 years. Cardy's conjecture had a respectable pedigree. In 2 dimensions, Alexander Zamolodchikov had proved an equivalent statement in 1986, the theorem, and it was one of those results that immediately felt like it ought to generalize. Cardy proposed the 4-dimensional version 2 years later in a short paper in Physics Letters B. Attempts to prove it came and went, some of them apparently succeeding and then failing on closer inspection, for the better part of a quarter century. This is the ordinary rhythm of the subject, and it is worth knowing about. A statement that seems obviously true, that everybody expects, that nobody can establish. In 2011, Adam Schwimmer of the Weizmann Institute and Zohar Komargodski, now at Stony Brook, proved it. The result is called the A theorem, and among quantum field theorists, it is one of the most admired pieces of work of the last few decades. They established it by working out how quantum fields are required to respond when gravity pulls on them at 4 separate points. And the proof carried a passenger nobody had ordered. It turns out that quantum fields in 3+1 dimensions cannot carry just any number of degrees of freedom. The mathematics permits only specific values. Scalar fields, the Higgs is the only one we have, carry exactly 1. Matter fields carry 5.5. Force fields carry 62. Komargodski's summary of that is worth quoting exactly, and nothing else works. 5.5. That is not a typographical slip, and it is not an average. It is the number of degrees of freedom a matter field is permitted to have, and it is not an integer. Tong's explanation is that fractional values arise when some of a field's possible variations are not fully independent of the variations of other fields. What one field is allowed to do depends on what another is doing, so the accounting comes out in halves. His way of putting it was that you kick that way, and suddenly all hell breaks loose, and the field is oscillating all over the place. Now do the sum. Komargodski counts the Standard Model as it stood before the Higgs field switched on and reshuffled everything, which is the cleaner starting point. In that configuration there are 4 scalar fields, one of which later becomes the Higgs we know. There are 45 fermion fields, left-handed electrons, muons and taus with their neutrino partners, right-handed electrons, muons and taus, and left and right-handed blue, green and red quarks of all 6 flavors. And there are 12 force-carrying bosons, the 8 gluons, plus 4 primordial bosons that later became the W+, the W-, the Z, and the photon. Antimatter is not counted separately here. It is already inside each fermion field's 5.5. 4 times 1 plus 45 times 5.5 plus 12 times 62, 995.5. That is how many degrees of freedom there are in the Standard Model. It is not a whole number, and there is no cleverness available that makes it into one, and Komargodski, who proved the theorem it comes out of, said this about the values it depends on. 1, 5.5, 62. They pop out of the theorem. I have no idea why this is what nature chose. I want to let that sit, because it is the emotional center of this stretch of the video, and it is easy to let it slide past as trivia. This is not a case where science does not yet know the answer to some difficult question. This is a case where science has a proof, the proof is respected, the proof is not in dispute, and what it says is that the number of fundamental ways the universe can vary is 995.5. the count of fundamental things, is not a whole number. The people closest to it are not embarrassed by this, and they are not hiding it. They simply do not know why. Tong's assessment of the whole situation, offered at the end, was not defensive. Underlying all of this is the statement that quantum field theory is unbelievably hard, and we're not very good at it. There's still a lot we don't understand. There is a further consequence of the theorem that quietly undermines the idea of a fixed inventory altogether. If degrees of freedom are lost as you zoom out, then the field content of the universe depends on what energy you are asking about. Tong put it directly: as you go down in energy scale, you lose particles, because they are so heavy they cannot form, and so you lose knowledge of them. Follow that all the way down, and at sufficiently low energies, only one particle survives, the photon, because it is massless and can carry arbitrarily little energy. Follow it in the other direction, and the early universe may well have contained fields that cannot be excited now at all. Many extensions of the Standard Model posit heavy right-handed neutrinos that could form in the first moments after the Big Bang, and can never form again. So the inventory of what exists is not only unclear, it is not constant across the history of the universe. So go back to the poster on the classroom wall. 17 squares, colored neatly, arranged for legibility. It is not wrong, exactly, but it is not a map of what exists. It is a decision about what to leave out in order to fit on a wall. Antiparticles folded away. 8 gluons collapsed into one square. Color dropped. Chirality dropped. Polarization dropped. And the actual mathematical content of the theory, replaced by a picture of small things in boxes. The poster is an act of editing. It always was. Most of us just never saw the unedited version. And there is one more question the poster cannot answer, and it is the question that finally takes the particle picture apart completely. Look at any one of those squares and ask something apparently simple. Where is it? Part 11. The thing you cannot point at. Where is it? Where is the excitation? This feels like it should be the easy question. Whatever else has been dismantled tonight, surely the thing we detect is somewhere. Detectors have positions. When a detector fires, something happened at that place. You may have to give up on the particle being a small hard object. Fine. But it is at least an event with a location. The theory does not grant even that, and it does not fail to grant it by accident. It has been proved that it cannot. The first result is called the Riesch-Schlieder theorem from 1961, and it is about the vacuum. Take the vacuum state. No particles, nothing there, the field everywhere, in its quietest configuration. Now restrict yourself to a small region of space-time. As small as you like, a cubic millimeter for a millisecond. You are only allowed to act on the field inside that region. The theorem says that from the vacuum, using nothing but operations confined to that tiny region, you can produce states arbitrarily close to any state in the entire theory. Any state. Including a state describing a galaxy on the other side of the observable universe. I want to be careful about what that does and does not mean, because it is easy to overread. It is not a recipe for building galaxies in your kitchen. The operations required are physically extravagant, and the theorem says nothing about performing them. What it says is structural. It says that the vacuum is not a blank sheet on which things are placed. It is a state so thoroughly entangled across every distance scale that a local disturbance in it is correlated with everything else. The vacuum has been shown, on the back of this, to violate Bell inequalities between regions that cannot communicate. Whatever empty space is, it is not empty, and it is not local. The vacuum's entanglement is not merely a curiosity either. It has become one of the load-bearing ideas in theoretical physics over the last 2 decades. The way entanglement in the vacuum grows with the size of a region, proportional to the boundary area rather than the enclosed volume, is the same scaling that appears in black hole thermodynamics, and it is the thread along which quantum field theory and gravity have been drawn closest together. That connection is a whole other night's material. For now, take only the narrow point. The quietest possible state of the fields is a highly structured, highly correlated state, and calling it empty is a convenience. The second result is sharper and more direct, and it belongs to the philosopher of physics, David Malamud, in 1996. He listed a handful of assumptions that any reasonable relativistic theory of particles ought to satisfy: that there is a well-defined probability of finding a particle in a given region, that measurements in regions too far apart to communicate do not affect each other, that energies do not run down forever, that the description transforms correctly when you change observers. He then showed that these cannot all be true at once. Not that we have not yet built such a theory, that no such theory can exist. Under those assumptions, the probability of finding a particle anywhere at all comes out as zero, which is another way of saying the assumptions were incompatible from the start. There is no relativistic quantum theory of localizable particles. There is a partial escape, and it is instructive precisely because of what it costs. Theodore Newton and Eugene Wigner constructed a position operator in 1949 that does allow a particle to be localized at a point. It works, and it is used. But the localization is not invariant between observers. A state that is sharply localized for one observer is spread out over a region for another observer moving relative to the first. Both are correct, which means position for a relativistic quantum particle is not a property of the particle. It is a property of the description. It is worth saying what physicists do about this in practice, because the honest answer is they work around it and get on with the job. Nobody at a collider is paralyzed by Malamud's theorem. Detectors are built out of matter. Matter is built out of fields, and when a field interacts strongly with a region of a detector, the detector registers something at that place. Localization is handled operationally. A particle is where it interacted, and that works perfectly well for every experiment ever performed. The theorem does not stop anyone doing physics. It stops a particular story about what the physics is describing. And there is a physical version of all this that requires no theorems at all, which is the version I find most persuasive. Suppose you try to pin an electron down. To confine something to a small region, quantum mechanics requires you to give it a correspondingly large spread in momentum, and by relativity, a large spread in momentum means a large spread in energy. Squeeze hard enough, and the available energy exceeds the cost of making new electron-positron pairs. So the attempt to localize a single electron produces additional particles. The scale at which this bites is the Compton wavelength. For the electron, about 2.4 times 10 to the minus 12 meters, which is roughly 1/100th the width of an atom. Try to specify an electron's position more precisely than that, and the question stops having a single electron in it. There is a companion result from the same era that belongs here, though I am going to hold most of it until later tonight. In 1955, Rudolf Haag proved that the mathematical setup physicists actually use to calculate, a device called the interaction picture, in which you treat an interacting theory as a free theory with the interaction switched on gradually, does not exist for interacting theories in any rigorous sense. The tool everybody uses is not a legitimate tool. Haag's own summary of the situation was that quantum field theory, in its standard form, is a set of rules with remarkable predictive power whose logical status remains unclear. Note the phrase, "and keep it." We are going to need it in 2 parts' time. You cannot point at one, not because your finger is too big, and not because the measurement disturbs it, but because there is nothing there of the kind that pointing requires. Notice what has happened to the word particle over the course of tonight. It started as a small hard object. It became one unit of excitation in a field. Then it became a unit that can be created and destroyed, that carries no identity, and that cannot be distinguished from any other of its kind, even in principle. And now it turns out it cannot be given a location either. At this stage, a reasonable person might ask what is left of the concept, and the answer is one thing. However badly the particle has done as an object, it has always been a reliable count. Detectors click a whole number of times. There is an amount of stuff in a region, even if you cannot say where in the region it is. That last footing is about to go as well, and it goes for a reason that sounds, the first time you hear it, like a mistake. Part 12. How many there are depends on who is asking. Imagine you are an instrument, not a person watching an instrument, the instrument itself, a particle detector, drifting in a region of space, so empty that the nearest atom is a very long way away. You are not moving in any accelerated sense. You are coasting, and you are reading nothing, not a faint signal, not a background hum, zero. The fields around you are in their quietest state. There are no excitations anywhere near you, and every needle sits at rest. This is vacuum, in the most rigorous sense the word has. Now something fires your engines. You begin to accelerate, steadily, in one direction. Nothing else about the region has changed. Nothing has been introduced into it. There is no source anywhere. And as your acceleration builds, your readout stops sitting at zero. Something begins arriving. At first, it is barely there, a warmth at the edge of your sensitivity, and then, as the acceleration climbs, it resolves into something unambiguous, a bath of particles, arriving from every direction, with a well-defined temperature. Not a signal from somewhere, a thermal bath, of exactly the kind you would read if you were sitting in a warm room. And alongside you, drifting, unaccelerated, is a second instrument, identical in construction, looking at exactly the same region of space at the same moment, and it is reading nothing at all. Both instruments are working correctly. Neither is broken, neither is mistaken. One of them is in a vacuum, and one of them is in a warm bath, and they are in the same place. This is the Unruh effect, and it was arrived at independently 3 times in quick succession, by Stephen Fulling in 1973, by Paul Davies in 1975, and by William Unruh in 1976, whose name it carries. It follows from precisely the same framework that has been correct about everything else tonight, applied to an observer who is speeding up. The temperature involved has a simple form. It is proportional to the acceleration, with the constants of quantum mechanics and relativity setting the scale. And the scale is brutal. To reach an Unruh temperature of 1 Kelvin, 1 degree above absolute zero, which is to say the coldest imaginable warm bath, you would need a proper acceleration of about 2.5 times 10 to the 20th meters per second squared. That is not a number worth leaving unpacked. Earth's gravity accelerates you at about 10 meters per second squared. A fighter pilot pulling 9 gravities is at about 90. This is 2.5 times 10 to the 20th. It is roughly 10,000 million times the acceleration you feel standing up. To get a signal large enough for a modern photon detector to register, you need an acceleration around a quadrillion times Earth's gravity. So the Unruh effect has never been observed. Neither has its close relative, Hawking radiation, and the two are the same physics wearing different clothes. An observer, hovering just outside a black hole's horizon, is accelerating to stay there, and what they detect is the Unruh effect in curved spacetime. Both are among the most confidently expected unobserved predictions in physics, believed because they follow inescapably from a framework that has been right about everything testable, and unconfirmed because the conditions are so far outside anything we can build. The attempts continue, and they are ingenious. There are proposals using analog systems, where a different physical medium is engineered to have the same mathematical structure so that the effect can appear at accessible energies. There are proposals using spin systems as quantum simulators of field theory in curved spacetime. There have been reports of acceleration-induced thermality in laboratory analogues. And there is active work on the second obstacle, which turns out to be as serious as the first. Even if you could accelerate something hard enough, the accelerating detector emits so much ordinary radiation that the UNRWA signal is buried. So recent proposals involve pairs of entangled detectors arranged to cancel the background coherently while leaving the signal standing. It is important to say what the effect is not, because the natural first reading is wrong. It is not a claim that acceleration manufactures particles out of nothing, as though the engines were paying for them. Nothing is being created by the acceleration in the way a collider creates particles by dumping energy into a region. What is happening is that the accelerating instrument does not have the same definition of the quiet state as the drifting one. The drifting instrument's version of nothing and the accelerating instrument's version of nothing are different states, and each reads a population where the other reads silence. The same logic explains something with much wider consequences. A universe that is expanding is a space-time that changes with time, and a space-time that changes with time has no single preferred quiet state either, so expansion populates fields with quanta. The universe does not need a mechanism to make particles in its early moments beyond the fact that it was changing shape. The fluctuations that seeded every galaxy we can see are usually traced to exactly this: quantum field modes stretched by inflation into something that did not stay quiet. There is one place where indirect evidence has been argued for, and it is worth knowing about even though it remains contested. Electrons circulating in a storage ring experience enormous proper accelerations, and their spins tend to align in a characteristic way over time, an effect named after Sokolov and Ternov. Some physicists have argued that the residual depolarization observed in such beams is an UNRWA-like thermal effect showing up in real hardware. Others argue that circular acceleration produces something related but not genuinely thermal, and that the case is not clean. The debate is still live, which is itself informative. This is a prediction so far from direct test that people are reduced to arguing about whether a subtle beam effect counts. But whether or not anyone catches it, what it says is the thing that matters tonight, and it is the last piece of the demolition. The number of particles present in a region of space is not a property of that region. Think about how strange that is compared with everything else we treat as physical. Two observers moving relative to each other will disagree about a lot of things. They will disagree about lengths, about durations, about simultaneity, about whether two events happened at the same time. Relativity taught us to live with all of that, but we kept a flaw underneath it. There is still a fact about how much stuff is there. The observers disagree about descriptions, not about contents. The UNRWA effect removes the flaw. One observer says the region is empty. Another observer, in the same region at the same moment, says it contains a thermal population of particles at a definite temperature. There is no experiment that settles which is right, because both are right. The disagreement is not about measurement error. It arises because defining what counts as a particle requires first choosing how to divide the field into vibrational patterns, and observers in different states of motion divide it differently. Particle number is defined relative to that choice. So the count is not in the world. The count is in the relationship between the world and whoever is asking. What is in the world, the thing both observers agree completely about, is the field configuration. That is the invariant. That is what is actually there. The particles were always a way of describing it from somewhere. We have now taken the particle apart entirely. It is not an object. It has no identity. It cannot be located, and it cannot even be counted objectively. What is left standing is the framework itself, the fields, and the mathematics that governs them, which has been right about every single one of these steps, which makes it a reasonable moment to ask how well that mathematics is actually doing. And the answer is not what almost anyone expects. Part 13. The theory that works and is not known to exist. Everything I have told you tonight rests on quantum field theory. The identicalness, the whole number excitations, the prediction of antimatter, the beam splitter, the exclusion rule holding the floor up, the census, the failure of localization, the observer dependence of particle number, all of it comes out of one framework, and that framework has a reasonable claim to being the most successful thing human beings have ever built. So here is the part that is not in the popular accounts. Nobody has been able to show that it exists. I mean that quite literally, as a statement about mathematics, and I want to walk through how the situation got to be this way, because it is not a scandal, and it is not a cover-up. It is just true, and physics has decided to live with it. Start with the infinities. When you set up a calculation in quantum field theory in the obvious way and start computing corrections, the answers come out infinite. Not large, infinite. The integrals you have to evaluate run over all possible energies, and the contributions from arbitrarily high energies do not die away. The response, developed in the late 1940s by Shinichiro Tomonaga in Japan and Julian Schwinger and Richard Feynman in the United States, working independently and in three mutually unrecognizable formalisms, is called renormalization. The idea is that the quantities appearing in your original equations, the bare mass and the bare charge of the electron, are not the quantities you measure. What you measure already includes all the field effects, so you absorb the infinities into the relationship between the bare and the measured quantities, and what is left over is finite and correct. It works to an accuracy that is difficult to overstate. It also made its inventors uncomfortable. Feynman later described it in print as a dippy process, and said that having to resort to such hocus pocus prevented him from proving the theory was mathematically self-consistent. Dirac, who started all this, never accepted it, and said so for the rest of his life. Freeman Dyson's contribution in 1949 was to prove that the three formulations were the same theory, which is what turned a set of tricks into a subject. The philosophical rescue came in the 1970s from Kenneth Wilson, and it is genuinely satisfying. Wilson reframed a quantum field theory as an effective description, valid up to some maximum energy, above which you do not know what the physics is. The infinities were never a sign that the arithmetic was broken. They were a sign that you were pretending to know about energies you have no business making claims about. Cut the theory off at a scale where you trust it, and everything is finite, and the cutoff's exact location does not affect predictions at accessible energies. That is the good news, and it comes with an admission attached. On Wilson's reading, quantum field theory does not claim to be fundamental. It claims to be right below a cutoff whose location nobody knows. There is a related warning sign that sits inside the theory rather than at its edges, and it is worth a moment because it makes the cutoff idea concrete. The strength of the electromagnetic interaction is not a fixed number. It changes with the energy at which you probe it, because the vacuum polarizes around a charge and screens it. Get closer, punch through more of the screening, and the charge you see is larger. This is measured, not conjectured. The quantity physicists write as the inverse fine structure constant is about 137.036 at everyday energies, and about 128.9 at the energy scale of the Z boson, and the change has been confirmed at electron-positron colliders. Extrapolate that trend upward, and the coupling formally becomes infinite at a finite energy, the Landau pole. That energy is so far above anything reachable that it has no practical consequence. But it is the theory telling you, in its own voice, that it cannot be the final description. Now the harder problems. In 1952, Freeman Dyson published an argument that the perturbation series of quantum electrodynamics does not converge. The perturbation series is the actual method. You compute the leading contribution, then the next correction, then the next, and each term is smaller than the last, and you stop when you are accurate enough. Dyson's argument was by contradiction. Suppose the series converges. Then the answer must behave smoothly as the coupling goes to zero from either direction. But flip the sign of the coupling and the physics becomes catastrophic. Like charges attract and unlike charges repel, so the vacuum becomes unstable and it becomes energetically favorable to produce more and more electron-positron pairs without limit. There is nothing smooth about that. So the series cannot converge, and its coefficients grow roughly like the factorial of the order. Dyson's own resolution has been universally adopted. Treat the series as asymptotic rather than convergent. An asymptotic series gets better for a while and then gets worse. There is an optimal number of terms, and computing beyond it degrades your answer. For quantum electrodynamics, the optimal point is estimated to be somewhere in the region of 137 terms, which is far beyond anything anyone will ever compute. The state of the art is 5, so the practical consequences are nil. The conceptual consequences are not nil. The most accurate calculation in science is the beginning of a series that does not add up to anything. Then Haag's theorem, which I flagged earlier. In 1955, Rudolf Haag proved that the interaction picture, the mathematical setup from which the perturbation series is derived, cannot exist for an interacting theory. The derivation is not merely unrigorous, its starting point is provably unavailable, and the calculations built on that starting point agree with experiment to 13 decimal places. And then the largest item. In the year 2000, the Clay Mathematics Institute named 7 open problems and attached a prize of $1 million to each. One of the 7 is Yang-Mills existence and mass gap. It asks for a proof that for any compact simple gauge group, a non-trivial quantum Yang-Mills theory exists on 4-dimensional space, and that it has a mass gap greater than 0. For the group describing the strong nuclear force, the mass gap part amounts to proving that glue balls cannot be arbitrarily light. Note what is being asked, not that the theory be extended, or refined, or unified with something else, that it exist, that there be a mathematically well-defined object corresponding to the thing physicists have been calculating with since the 1950s. Experiment says the mass gap is there. Lattice simulations, which chop spacetime into a grid and compute numerically, reproduce the masses of protons and other composite particles to within a few % from first principles. That is powerful evidence. It is not a proof. Constructive quantum field theory did succeed in rigorously building interacting theories in 2 and 3 spacetime dimensions in the 1960s and 70s. 4 dimensions, which is to say here, has resisted every attempt. As of 2026, the only one of the 7 millennium problems that has been solved is the Poincaré conjecture. The Yang-Mills Prize has been sitting unclaimed for 26 years. And there is one more absence, which I promised earlier I would come back to. Gravity is not in the framework at all. It is not one of the 17 fields, or the 118 states, or the 995.5 degrees of freedom. Every attempt to treat gravity the way the other 3 forces are treated runs into infinities that renormalization cannot absorb, because gravity's coupling grows with energy rather than settling down. So the claim that everything is a quantum field is not yet a claim about everything. It is a claim about everything except the force that is currently holding you to your bed. Remember the instrument. One continuous instrument filling all of space, and then 17 of them layered over one another, and everything that has ever happened being what they do. That image has done a lot of work tonight. Nobody has proved that instrument can be built. Which brings us, finally, to the question I promised at the beginning, and to the answer. Part 14. What you are. Before I give you the answer, I want to clear one thing out of the way, because a framework this strange attracts company, and you will have met some of it. The first is the claim that because the vacuum has energy in its lowest state, the point I asked you to keep in your pocket several hours ago, that energy can be extracted and used. Free power from empty space. The answer is short. The 0-point energy is the ground state. It is the lowest energy the field can have. Getting energy out of anything requires it to drop to a lower state, and there is no lower state. That is what ground means. The measurable effects are real. Two very close metal plates in a vacuum are pushed together by a genuine force, predicted by Hendrik Casimir in 1948 and confirmed by Steve Lamoureux in 1997 to within about 5%. But that is a static force, not a supply. Let the plates snap together and you get a one-time release of energy, and then you have two plates touching. Nobody has ever produced net energy from the vacuum, and the theory is quite clear that nobody will. The second is the family of claims that because everything is fields, consciousness is a field, or that intention reaches across space because everything is connected. The honest reply is that the word field is doing completely different jobs in those two sentences. The fields of the standard model are specific mathematical objects with measured coupling strengths, and there are no couplings to anything resembling intention. What is genuinely true, that the vacuum is entangled across regions, which we covered earlier, does not permit signaling of any kind, because no local measurement can be used to send information. The strangeness is real. The conclusions people hang on it are not. Right, now the answer. Lie still and consider yourself at the level at which the physics actually works. You are not a body made of parts. There are no parts. There are fields, filling this room, filling the space between you and the ceiling, continuous, everywhere, with no gaps and no edges. And you are a disturbance in three of them. Up quark, down quark, electron. That is the entire inventory. Every thought you have ever had, every memory, every sensation in your hands right now, is a configuration of excitations in three fields, held in a particular shape. And the shape is the only thing that persists. The excitations do not. They are exchanged with the room continuously, and more importantly, they carry no identity to lose in the first place. There is no fact about whether the excitations constituting you tonight are the ones that constituted you a decade ago, because there is nothing in the world that could make that sentence true or false. Electrons have no serial numbers. The question cannot be asked. Notice what is not being claimed there. It is not that the excitations are being swapped out fast, the way the familiar version of this idea usually goes, that the atoms in your body are replaced every 7 years, or whatever number the article used. That version is true, and it is far too weak. It still imagines a stream of little objects flowing through you, each one a distinct item, arriving and departing. There are no items. There is a field, there is a number of excitations in it, and the number changes, and no ledger exists anywhere in the world recording which was which, because the theory has no place to write one, and neither does nature. So the honest description of a person is not a collection of matter. It is a pattern that matter passes through, except that even matter is the wrong word, because there is no material substrate underneath. There is a field, and a shape it is holding. If that sounds like it should be distressing, notice that it is exactly the same relationship a wave has to the ocean, and we do not find waves distressing. A wave is not made of particular water. It is a shape moving through water, and the water it passes through is different every second, and the wave is entirely real. What field theory does is remove the ocean and keep the wave. Faraday's field survived the death of the ether, and here at the end, so do you. I should be fair and say that not every physicist reads the framework the same way, and the disagreement has survived for 80 years without anyone winning. Some take the strong version. Fields are what exist, and particles are bookkeeping for the whole numbers our detectors happen to produce. That is the reading the mathematics most naturally supports, and the one most working theorists default to. Others take a deflationary line. Quantum field theory is a machine for predicting the results of experiments. Questions about what is really out there exceed its remit, and the field is as much a piece of formalism as the particle. Haag's theorem and the missing four-dimensional construction give that view real teeth. And others take the emergent line, which we will come to in a moment. What all three share is the negative claim, and the negative claim is what tonight was actually about. Whatever reality is at bottom, it is not a collection of small, persistent objects. Every version of the theory rules that out. The disagreement is over what to put in their place. There is a reason I have kept coming back to the instrument. One continuous instrument, everywhere at once, and then 17 of them, laid over each other in the same space, and everything that has ever happened being the sound they make. Every star, every collision in every accelerator, every conversation. 17 instruments, and nothing else, and you are a sustained note. And nobody has proved the instrument can be built. That is the part I would ask you to keep, because it is the part that keeps this honest. The framework that says all of the above has a divergent series at its heart, an interaction picture that provably does not exist. No rigorous construction in the number of dimensions we live in. $1 million sitting unclaimed since the year 2000, for anyone who can show it, is mathematically real, and no account of gravity whatsoever. It is simultaneously the most precisely verified description of the world ever produced, and an unfinished piece of mathematics. Both of those are true at once, and the physicists closest to it say so freely. Quantum field theory is unbelievably hard, and we are not very good at it. There is still a lot we do not understand. So the poster on the classroom wall was never a map of reality. It was an act of editing. Small things in boxes, because small things in boxes are what a wall can hold, and because it is how all of us learned to think before we knew there was an alternative. Here is what is behind it. There are no objects. There is no smallest thing. There is nothing hard at the bottom of anything, and never was. There are fields filling everything, and quantized disturbances in them that we count and name and treat as furniture, which cannot be told apart, which are created and destroyed constantly, which cannot be assigned a location, and which cannot even be counted the same way by two observers moving differently. The world is not made of things. It is made of something doing something, everywhere, all the time. That is the idea. That is the one that reorganizes everything else you know about the physical world once it goes in. If you don't understand this, you don't understand reality, and now you do, or at least you understand the shape of it, which is as much as anyone has. I have one more thing to leave you with, and it is not a conclusion. Everything I have described tonight is, by its own admission, an effective description, valid below a cutoff. Nobody knows where the cutoff is, which means fields might be exactly what the poster was, the right way to talk at the resolution we can currently reach, and a simplification of something we have not seen yet. Photons in a crystal behave in every mathematical respect, like elementary particles, and they are nothing but the collective motion of atoms. If our fields are the same kind of thing, the behavior of some structure below them, then this whole night has been a description of the second to last layer, and somewhere under that, if there is anything under it, is whatever is actually doing this. Sleep well,